Hi Netrasri. Hello. Hello. Oh, I'm audible, right? Yeah. Uh, Thanks for waiting with patience. Think you can see the screen, right?
Yes, sir.
Yeah, fine. Sorry. Yeah. Uh, till now, what we have discussed was we have discussed I think five weeks courses where we have discussed the what is the difference between open system and closed system, and then how to derive the equations for the closed system as well as for the open system. And once we have discussed the closed system and open system, we have discussed that how to go through Maxwell relations, like when you want to find out the desired properties based upon any two variables, how to find out either internal energy, entropy, or enthalpy, how to find it. And then we have gone through the ideal gas situations, PV by RT, and for other virial equations, starts from Van der Waal, Redlich, Kong, and other equations. And then we have gone through the zeroth law and first law and second law, and then we have gone through the basic formula, basic questions which we need to solve, and then we have gone through the fugacity coefficients, and in the last class we have gone through the Jacobian methods, and we have already seen the partial molar properties, and we will use some of the partial molar properties, like a little bit, one or two formulas in this class. And then I think this is the things which we have discussed as of now. Uh, so G by RT, we have discussed the residual properties, and what is the difference between residual properties and all the fugacity coefficients. And I think the week 6 class comprises of, yeah, we will go through this question at the end of the class. I think this is the question you have the doubt, right?
Yes, sir.
Yeah, we will go through this question at the end of the class. So I think for the today's class you will understand, uh, I mean, you will get one clarity. So in today's class, what we are going to discuss was, I will just make one rough sketch. Because today's class will be more really depend upon the equation, so that's why I didn't make any PPT. So because we thought that it will be helpful to rewrite the equations. So in today's class, we will talk about the phase equilibria, then Rolle's law.
So we can see your basics.
Okay, thanks for telling me in the starting itself. I think today there are some issues with my system, so bear with me for today's class. I will rectify it after the class. You can see the screen right now.
Yes, sir.
Okay, fine.
Yes, sir.
Uh, in today's class, we will go through the phase, sorry, uh, the sixth week content of phase equilibria, Rolle's law, and there are other activity coefficients. How to get the activity coefficients? What do you mean by activity coefficients and all the things? Where we have the Redlich, I think Kister equation, and then we have the Van Laer equation, then we have the Margulis method, and then we have the Wilson equation. So activity coefficient for the excess properties. So today we are all going to talk about the vapor phase liquid equilibrium. So it is nothing but vapor liquid equilibrium. So before going into the class, okay, so now we will start the phase equilibrium. So these are the today's contents. What are the phase equilibrium rules law? Whatever you are applying, we are not going through we are going through the vapor and liquid phase. So you know already degrees of freedom, right? If I am talking about the degrees of freedom, as we discussed in the last few classes, F equal to 2 minus pi by n. So if I say that we have phase liquid equilibrium of one component, so can you tell me what will be the degree of freedom? Sorry? You understand this one? Hello?
If it is one component, then chemical physics also one, right?
One second. Can you repeat the question, because the voice is getting echo here?
If it is one component, then the phase should also be one, right?
No, what I'm saying was, I've said is two phases. Say suppose the example is water in liquid vapor. Water and liquid vapor phase. So now you have two phases, right? The component is one.
Okay.
So you understand the degrees of freedom, right? So how we are going to talk about the degrees of freedom? So basically you understand how the degrees of freedom is calculated, right? Now we will come through the chemical equation equilibria. So any doubts in the degrees of freedom? In the basic degrees of freedom, we will go deep into it. For now, any doubts for the vapor liquid equilibria? If I take any of one component, say if I take two components, it will be F equal to 2 minus 2 plus 2, F equal to 2. Any doubts in this? How we got 1 or how we got 2?
Yeah.
Okay, fine. So now we will go through the phase equilibrium diagram. So we have liquid, gas, solid. So basically we have here what is the diagram we have? We have three phases. Okay, one is solid phase, liquid phase, and the gaseous phase. Say 1, 2, 3, and this curve is dividing this all the three phases into two phase diagram. Say suppose if I take the liquid gas, what does it says was this line is nothing but a coexistence line. Coexistence curve. So what does it say? So at this line, on this line, the degrees of freedom will be F equal to. Can you tell me anyone what will be the degrees of freedom on this line? Obviously, we are talking about only one component system. Don't think about more components. We are going with the one component system. If it is one component system and I have taken this line, so can anyone tell me what will be the degree of freedom on this line, on this curve or line? Two minus. You understand, right? How this curve one came?
Yes, sir.
Okay, fine. So if you take any two, say suppose if I take solid and gas, so here also it will be 1. If I take solid and liquid, here also it will be F equal to 1. So what we are doing was, we have three phases, solid, liquid and gaseous phase, and the phase diagram is converting this diagram into the two phases diagram with the degrees of freedom 1. So if I want to make a statement, we have three phases, which is going to which is undergoing to two phases by phase diagram with degrees of freedom 1. Okay, so any questions in this, any doubts in this statement? Okay, I assume there are no doubts. Sorry.
No.
Okay, fine. So in the next question, what we are doing was, so in the last class we have seen the chemical equation equilibrium, right? Chemical equilibrium, chemical reaction equilibrium, where I says that mu mixture will be less than mu of pure. So then the system wants to go from mixture to pure until, sorry, mu A wants to go to the mu mixture, so until mu mix equal to mu A. You remember this from the last class? So basic example of this was, if I take a solid and liquid, the solid will get melted until the mu of solid, if mu of solid is greater than mu of liquid, what does it say was mu is solid less, so then solid wants to go into the water shape, so that's why it is getting melted. But if you have mu solid equal to mu liquid, this is nothing but the equilibrium case, where we have there will be no transfer of phases between these two. Okay, so at equilibrium we say mu s equal to mu l. So if you come back to this concept, can you tell me what is happening at this coexistence curve? This coexistence curve is nothing but the equilibrium condition. Make it here itself. So now the coexistence curve. So if I take the liquid and gas, so this is nothing but the equilibrium, and this is nothing but equilibrium. This line is equilibrium line. So what does it says was, on this line alone, the particle can either be in the liquid phase and the particle can be in the both liquid phase and the gas phase. That's why you are taking the phases as 2. Okay, if I increase the temperature or pressure, say suppose if I take the water, and it will be in the, say suppose solid and liquid phase. If I increase the pressure by some amount, it will be there. If I keep the suppose, how to say it, if I take solid and liquid of water, you assume that this is the case, and assume that this is the point of here. So this is point here. Okay, on this coexistence curve it will be stays as mu s is nothing but mu l. Once
Sir, you are not audible.
I am not audible. Am I audible? Hello? 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 Hello?
Yes, sir.
Yeah, you can hear me, right?
Yes, sir.
Okay, fine, thank you. Because somebody said that I am not audible, that's why. Just let me know, okay, if I am not audible. Because okay, fine, thank you. You can see the screen, right?
Yes.
Okay, fine, thanks. So you understand what I'm trying to say was, right? So sorry, one second. So what I'm trying to say was, on the coexistence curve, the value it will be in the equilibrium. That's why we have the both solid and liquid. So say suppose from here, if you either increase the temperature, it will become as liquid. Then the degrees of freedom will be F equal to 2 minus pi plus n. It will be nothing but 2 minus 1 phase plus 1. It will be 2. So it will come as 2 phase. So 2 degrees of freedom is 2. If you decrease the temperature, it will go to the solid. Okay, understand, right? So suppose if you have taken water and ice, just take the, sorry, if you take just if you take the water and ice, if you decrease the temperature, it will go all to the solid phase. And if you increase the temperature by keeping the constant pressure, it will all goes to the liquid. So you understand this curve, right? So what does this curve do? So you understand, right, what is the coexistence curve does?
Yes, sir.
So now we'll discuss, okay, how does this vary? Say suppose why the values are like, if I see the curve, why the liquid curve is like this, why the solid curve is like this, why the gaseous, sorry, yeah, solid and gas curve is like this. Say suppose for that we will have the phase equilibria. So in the phase equilibria, say suppose we need to find out the graph is between the pressure and temperature, right? So we need to find out how the pressure is changing with respect to the temperature. So if you know the mnemonic diagram, keep in the mind that how to draw the mnemonic diagram, it will be very helpful for you. And if you know any one equation, TdS minus PdV, it is V P S T. So we want to focus on the change in the pressure with respect to the temperature. So that is the equation will be given best by Gibbs energy. So we already discussed that every extensive property of molar we know that say suppose I have enthalpy, the molar enthalpy property will be Hi. I have entropy, the molar property will be Si, but for Gibbs it will be mu I. So this we have seen in the last class. So now what I will write was, I will write the delta G equal to minus S delta T please V dP. So you understand, right, what I am doing? So if I am taking out the coexistence curve, so what I am doing was, I am dealing with the coexistence curve. So coexistence curve, what we are saying was mu1 equal to mu2, solid is equal to liquid. So it means d mu solid will be equal to d mu liquid. For the rise in, say suppose from here on this coexistence curve, on this coexistence, if I take, I have taken this line of solid and gas, and I am at this point initially, ith point, and second point I increase the temperature from 1 to 2. So then we will get T plus dt. So then we will have the increase in the chemical potential also. So but as we are in the coexistence curve, the ut is equal ut of solid is equal to u of liquid. So it means minus S dt plus V dP of solid will be equal to the liquid one. So now, sorry, gas, I'm making mistake. If I am talking about the solid and gas, you can either do the same thing for solid, liquid, liquid vapor also. So now we have this, and say suppose we are going from alpha to beta. So it means what we have is minus of, one second, yeah, minus of S alpha beta minus S beta dt plus V alpha minus V bt dP of solid is equal to gases. I'm not taking, I'm taking both sides. So now this equation will at the entirely it will become as dP by dt. If I take this side, it will be delta S by delta V, changes from the solid to gas. Any doubts in this equation? How this equation came? Am I audible? Hello?
Yes, sir.
Okay, fine. So you have no doubts regarding this equation, right? So what does it says was, we have the equation of dp by dt equal to delta S by delta V given from solid to gas, or say suppose solid to liquid, or we have liquid to gas. Okay, so now we can understand that how the entropy changes and how the volume changes. So based upon these two changes, we have the curve, coexistence curve like this, the steep one for the solid liquid. So why it was, say suppose we are going from solid to gaseous. So for solid, the orderness of the entropy is based upon fully on orderness. Okay, for solid it will be packed, and for the gases the molecules are disorder. It will be in the higher order. So it means delta S is far greater than 0, and the volume too. So volume of a container of a small ice cube is different with the volume of the gas. So delta is also greater than 0. So that's why we have the delta S by delta V will be greater than 0, because they both are higher, and the delta S will be much more higher than the delta V. So that's why we have this curve. And once after this, if you go for the liquids to the gases, there will be disorderness from the liquid to S, but it will be comparatively less when compared with solid to gases, and still this will be more. So that's why we have the slope of the graph of delta S by delta V will be greater than 0, but it will be steepest one, not the steepest one, the slope one, silent one. But if you take from the solid to liquid, the delta S will be much bigger than 0, but delta V will be so. So that's why we have the steepest one. So any doubts in these equations? Why these equations came?
Sir, can you explain this concept again?
Okay, fine. So I will write it here itself. So you understand this equation, right? dp by dt equal to delta S by delta V.
Yes, sir.
For solid to gases, for solid to, I mean, on the coexistence curve, it says the coexistence curve, or for the solid to liquid, or for the liquid to gases. So now I taken the example of liquid to gases, liquid gas coexistence curve. So now I want to plot the curve. So how the curve will be? So for that, we know that liquid molecules and the gaseous molecules, if I take both systems, the disorderness will be here also, there will be disorderness of the atoms inside it. Here it will be more random. So it will be the delta S is greater than 0, because here it will be more higher. So delta S is nothing but S gas minus S liquid, right? So the gas will be higher than the liquid, so it will be greater than 0. So delta S is greater than 0. And the volume, the liquid volume of the water is very smaller than the liquid water of gas. So it will be volume of gas is always greater than volume of length. So it will be greater than 0. So overall delta S by delta V will be greater than 0. But as a delta compared to both, this value is higher in this case compared to this value. So the graph will be positive slope, but it will be like not the steepest one like this, it will be goes like this with minimal changes. Okay, so this is for the liquid to gases. So once you have the liquid to gases concept, then we will go through the, I will keep this one in the middle as it is. So then we are going for the solid to gases. So now if I take the solid and the gas, here the molecules are tightly packed. Here there will be random disorderness will be higher in the gas molecule. So the delta S will be far greater than 0, and the delta V is also far greater than 0. So delta S by delta V will be greater than 0, but here the both components are higher than the 0. The value will be like this. When we comes to the when we comes to the solid to the liquid, so it is tightly packed, the liquids are freely disorder, but here you can see delta S is greater than 0 but not much greater than the here, and here delta V will also be greater, here delta V will be greater than or equal to 0. See, if suppose you can take it like this, uh, take a small cube of water, how to say it, ice cube, and if you put it in the tray of ice, we can see that the volume occupied by the solid will always be more or slightly lesser than the volume occupied by the liquid. So that's why I given the volume as delta V greater than 0, greater than or equal to 0. So here it is greater than 0, but here this component is much bigger than this one. So that's why we have the graph of the steepest one. So this is the way how we got the phase equilibria, liquid, gas and solid. Okay, if you take anything for the setup of ammonia or methane or anything, this will follow this, and the triple point is here, at 0 degree Celsius, sorry, 0.01, I think 273.15 Kelvin, 273.15 Kelvin. So this is how, based upon the entropy and volume, how can we plot the phase diagram. So any doubts, or do you want me to explain again? Hello, am I audible?
Yes, sir. No doubts, sir.
Okay, fine. So we have that Clausius-Clapeyron equation. Okay, so what does it says was, so we have, we know that G equal to H minus Ts. So G is like, we know that at equilibrium it's nothing but mu1 should be equal to mu2 at equilibrium. So I have taken H alpha minus T of S alpha is equal to H beta minus T of S beta. So I'm saying one component is going from alpha to beta, so then it will be H alpha minus H beta equals to minus T of S beta minus S alpha. So it will be of H beta minus H alpha equal to T of S beta. So from the previous equation we know that delta P by delta E equal to delta S by delta V. So here I am taking delta S as delta H by T. So I will put this here, so it will become as, okay, this is the Clausius-Clapeyron equation which you are seeing. And what is the, whatever the delta S and delta V, and how delta V is greater than 0 and delta S is greater than 0, these all are the assumptions carried out by this equation. So any doubt how we get this equation?
Yes.
Fine. So if there are no doubt, then we can derive the equation. So for, we know that dP by dt equal to delta H by delta V. So if I say, if I am consider about the gaseous phase, the volume will be much more greater than 0 compared to much bigger than other phases, whether solid or liquid. So this equation will go to dP equal to dTH by V gaseous. If I take the ideal gas situation, if, then this equation will will be like delta H by T into RT by P. So it will be P delta H T square R equal to dP by dt, and this equation will be dP by P equal to delta H by R dt by T square. Any doubts in this equation? Hello? Hello? Am I audible?
Yes, sir. No doubts.
Okay, fine. Because I thought I'm not audible, so that's why. Okay, fine. So from this equation, I think we need to space the space. So we have dP by P equal to delta H by R dt by T square. So which gives of d of ln P equals to delta H by R dt by T square. If I apply the integration on both sides, it will be ln P2 minus ln P1 equals to delta H by R. It will be minus 1 by T. Minus 1 by T, if I take the LCM and all the things, it will be T1 T2. Hello, T1 minus, it will be T2 minus T1. So this will be the, and if you take the ideal gas, this will be get standard. So then it will be dH by dTR T2 minus T1 T2. So this is the relation between pressure and pressure versus temperature. Any doubts in this equation? With this we completed the phase equilibria, the basic version of phase equilibria. Any doubts? How we can get the
No.
how we can get the in phase equilibrium? You need to understand that how the Clapeyron equation assumptions were done, and then how can we get the relation between delta S, delta V, and delta H, and how we got the P versus T. Okay, if you see the phase equilibria, I am talking about the only one component system. Say suppose you have the water. What I have done was, say suppose if I keep like this, what you assume was it is in the coexistence curve, so that's why you have the water, and the here water in liquid form and water in vapor form. What if we have air here, which means we have another any inert gases? So how does the equation changes? Any idea how does it changes? So what we can do was, you can take the again you can take the partial pressure. So here in the liquid, say suppose it is the water, I am assuming it as A. So now if I make this diagram again, it will be like PA. Here it will be PA in the gas phase plus inert gases will be there. So now at equilibrium, if I am taking about the equilibrium, this will be also equal to equal, because we have the mu1 equal to mu2. So what does it says was, this total, here it is total. So P total is nothing but PA plus P inert. So what we have was, at equilibrium condition, mu of gas phase comma T comma P total is equal to mu of liquid phase comma T comma PA. Any doubts in this equation? We have taken the gas phase, the top one, temperature and the Holt pressure, mu of liquid comma temperature comma pressure of this one. So then we will solve it. Say suppose we will do the du by dpt. Here I will do this, and here also with respect to the temperature constant, here also I am doing dpa at the rate temperature. So but here what I will do was, for the clear understanding, what I will apply the chain rule here. So what you will get was, because here in the gas phase we also have the dpa, right? You can see. So dpa by dpt, they both are at constant temperatures, okay, equals to du by dpa at constant temperature. This is in the gas phase, this is in the liquid phase. You need to remember this one. So we already know that dg by dp at constant temperature equal to volume. So this will be molar volume of the gas into dpa by dpt. It is equal to molar volume of the liquid. So now dpa by dpt will be, so any doubts in this equation, how the pressure varies with respect to the total pressure if you have more than one component? And this will always be greater than 0, because volume of the liquid will never be 0. This one will also will never be equal to 0, so it will be greater than 0. So then you will have the graph of if I plot PA with respect to the P total, start from some point, it will increase. Any doubts in this equation, how we got it? Or if you want me to explain again, I'll explain it again.
Sir, can you explain?
Okay, fine. Say suppose as of, if I'm talking about the phase diagram, we are talking about only one component system. If you remember, I am talking about water in liquid, water in vapor, or if I say suppose solid, water in solid phase and water in liquid phase. But what we have a system, say suppose here we have water and here we have water. Basically, if I'm talking about a ideal, in general pure mixtures, we have one component system, we have only water. But what if I say we have another air molecules, where it has some any random molecules with, if I say it has inert gases. So now how does this pressure changes? Which pressure will be higher, which one will be lower? So for this, what we can try to understand was, because whatever the previously we have discussed, that pressure in relation with the temperature is at only one component system. So now here what we will do was, we need to understand how the pressure of A here changes with respect to the total pressure. So for this, what we will do was, here we already have two phases, liquid and vapor. If at equilibrium, we know that mu L equal to mu V. Okay, so now I can write it like this: mu of liquid phase T of pressure of A. Pressure of is nothing but pressure of molar pressure of water. It is equal to mu of gas, gas comma T comma P total. Okay, so P total equal to PA plus P of remaining. I can put it as remaining. Okay, so now we have the mu of liquid comma T comma. So now I will do d mu by dP, mu of the liquid phase comma T comma PA with respect to the PA here at constant temperature will be equal to d mu of gas at P total by dPT at a constant temperature. So this will be, we know that as mu is nothing but G, we already know that G equal to minus TdS plus VdP, then dG by dP at constant, SdT at constant temperature will be equal to V. So here it will be V of liquid. So it will be V of liquid, molar volume liquid, because we have the mu. So here I will do the chain rule. So what the chain rule do was, dPA at constant temperature, dPA by dPT at constant temperature. So this will be VL. We know that this will be the gas phase. The same thing if we do. So we know that the volumes will never be less than 0, so it will always be greater than 0. So that's how we get these values. If the total pressure, if there is nothing, then it will be pure species. I mean, if we have only PA in the both the cases, then it will be a pure species. So it will be somewhere here. So it will increase by go on. So any doubts? How the pressure changes if we have any other new component? So we have gone from phase equilibria. We have taken the case of phase equilibria. Then we are moving that. Okay, what if we have new pressure? So any doubts? How does the pressure changes, and what are the parameters it affects? I'm audible, right? Hello.
Yes, sir.
Okay, thank you. So now what we will do is, say initially we have only one phase, water in liquid, water in vapor. This is nothing but phase equilibria. Then we discussed water in liquid, water in vapor plus X molecules. Now what we will do was, we will take water in liquid, let's say suppose any component, the methanol or ethanol in liquid, we will take water in gas plus ethanol in gas. So say suppose it's like A of L comma B of L comma A of gas comma B of gas. It's nothing but XA, XB, YA, YB. Okay. So what will happen? Say suppose I have two systems. If I take ideal solution as one as volatile and other one as non-volatile. You can take the example of sugar and water, salt and water, and this type of example. So what will happen was, if I take that example, say initially if I take the molar fraction of say sugar, if at the zero, it will be the only pure species of water. Okay. If I increase it, it will go like this because of the we have the Rolle's law from here. From the Rolle's law, what it says was, it's nothing but 1 minus xb pb star pa star, sorry. As you increases xb, the value of this will go less, so that's why it comes to 0. So when it becomes 0, pa will be nothing but pa call. Then as you increase xb is goes to 1, pa goes to 0. As xb goes to 0, pa goes to pa star. So any doubts in this equation?
No, sir.
So now what we will do was, now we will take both as both volatile compounds. So both volatile compounds. So what does it says was, I am taking the xb. So we know that pa equal to xa into pa star slash pb equal to. So from Rolle's law, Dalton's law is different. Dalton's law is nothing but pa equal to xa into total pressure, p total. Here it is pure species. Okay, the total is different with the pure. Okay, you need to remember the difference between Dalton and the Rolle's law. Okay, the basic difference between Dalton and Rolle's law is, Dalton discuss with the whole temperature. He will tell about that P is equal to, he says that for Dalton it will be Pa equal to xa into P total. For Rolle's law, Pa equal to xa into P pure. This is pure and this is total. Okay, you need to remember the difference between the Dalton's law and Rolle's law, and say that this is the condition. If I take the suppose two components where the pressure of pure molar pressure of A is higher than the pure molar pressure of B, so it means at xb equal to 0 we have only Pa, so it will be pure Pa, so it will be around here Pa star. Say suppose at xb equal to 0 we will get Pa equal to Pa star. At xb equal to 1 we got Pb equal to Pb pure, and there is one more condition which says that Pa is greater than Pb, so it will be around here. So here the Pa will be here, and if this is at xb equal to 1, this is at xb equal to 0, and if I say suppose if it is xb equal to 0, the Pb will be here. So if I make the both lines, so the Rolle's law says that if it is ideal gas, then the total pressure will be equal to this one. I think this is the Rolle's law says, yeah, P total equal to Pa plus Pb, which is nothing but Xa Pa star plus Xb Pb star. If you're saying that the system obeys the ideal law condition, ideal gas condition, then ideal laws, then it should obey the Rolle's law, which says that whatever the curve it is, it should be this one. It is nothing but again coexistence curve. If you see, it says that resonant expression, beyond this it will be liquid, it will be gases, but below this point we are not talking about the gases because we are talking about the mole fraction of the liquids. For that we need to consider the point of YB comma YA, okay, to be the liquid and gases. So this is also coexistence. At this point on this coexistence curve we have the liquid and gases. If it is beyond this point it will be liquid, and if it is less than this point it will be gases. So this is the phase diagram if you have two molecules and if something obeys the ideal laws and if it follows Rolle's law. Any doubts regarding the mole fraction? And this line is nothing but bubble line. If you're not getting, you can ask me, I will explain it again, because yeah, bubble line. Any doubts in the bubble line? Bubble line deals with pressure versus mole fraction, XA/XB. Any doubts regarding this bubble line? So I'm audible, right? I think I'm audible. So I am audible, right? Hello. Hello Netra or Fahima, can anybody tell me whether I am audible or not? I think there is a net issues. Hello. Hello. So am I audible? I think so. I am audible. Hello Fahima. Hello. I think am I audible?
Yes, sir.
Thank you. So for the boundary layer condition, this will be the case. I mean for the bubble line. If I am talking about the dew line, if I am talking about, so that is the bubble line is for pressure versus XA or XB. Say if I take the graph, and we know I am already discussing that PA star is greater than PB star, which says here it will be PA star, here it will be PB star. If I am talking about the mole fraction, the graph slightly goes like this. So here it will be P of PA plus PB, it will be YA into P plus. So this line is nothing but dew line. So you know, right, bubble line deals with pressure with XA comma XB. The dew line deals with pressure of YA comma YB. Any doubts in this?
No, sir.
Okay, fine. So now, you know, this is the basic condition where we will be using the distillation process. So in the distillation process, what we will do was, we have say pressure and I am taking the mole fraction. If I take the mole fraction, this will be the Rolle's law, which says bubble line. And if I take the mole fraction of the gas in the gas phase, this will be like this. As I said, this is the again composite curve for the liquid and gases. So consider the situation where we have the only mole fraction and we are squeezing it. We are decreasing the pressure. So suppose we are at this point, it is all liquid. We are squeezing, and the liquid consists of both XA comma XB at this position. At this position, suppose this is the A position. In the A position, we have XA comma XB. We have both, and we are squeezing, we are squeezing, we are squeezing, we are squeezing until this point. We got into this. After the squeezing, it will never go down because we are talking about the water, right? Mole fraction of how to say it. It will go in this way. If you are increasing, if you are taking this curve, if you are taking the gaseous molecule, it will go like this and it will go like this. For the distillation, what you can do was, you can go from the gaseous point, you can increase the you can increase the pressure. So what do you mean by increasing the pressure? We know that PV is inversely proportional to pressure. So if you are saying increasing the pressure, is nothing but volume is decreases. So if I increase the pressure, the volume is decreasing. So what you can do was, you have the gas molecules, just try to squeeze it, squeeze it, squeeze it, squeeze it, and when you are squeezing it more at the constant temperature, it will get condensed and the water it starts to form the liquid. And if you are, say suppose you have the liquid in this box at this position, I'm talking about the, say suppose this has B and this has A position. If I'm considering the A position, from A you need to decrease the pressure, from B you need to increase the pressure. It means volume is increased, volume is decreased. So now take the box and of this and try to increase the volume. What happened was, so this space is nothing but here, so it will have the water, the remaining will be of vapor. So here also same. So if I take the box like this, and initially we have the gaseous phase, this is all gases. So what it happened was, if you squeeze it, it will become small shape. After squeezing it, the molecules will get trapped on the condensed part, so that will form as liquid droplets. And if you squeeze it more, squeeze it more, squeeze it more, you will have the liquid and the bubbles. So that's what here we are doing. So distillation process, what you will do was, you will increase up to the coexistence curve, then you will condense it. So then it will go, from this point to this point. Then from again here you will have at this point, and from this point again you will increase the pressure, you will be at this point. From this point again you will condense, you will get at this point, and then this is the point. From this point again you will increase like this. So this way you will get the distillation process, you will get the pure PB out of the mixture. You will get from the gaseous phase, the blue line depicts the PB pure. And from the liquid also you can do the same thing. You can come here this path, you can go like this, or you can got my point, right? What I'm trying to say, you can come here like this, and this. You understand, right, how the distillation process happens with respect to the Rolle's law. With regarding to the bubble line and dew line. Any doubts in this concept?
Yes.
So then we have the equation, so which from the Dalton's law we know that this is on the Dalton's law. Rolle's law we have, so P star. So now we need to make P A star, P B star. So now we have PPB. So now if I want to make everything in terms of YA and XA, it will be XA PA star plus 1 minus XA PB star PB star minus x star is equal to XA PA star PB star plus PA star minus PB star by XA. So this is the equation for the molar, how much the mole fraction of A is converted to the gas phase, from the liquid to gas phase. So any doubts in this equation?
No.
Okay, so now we if you have no equations, then we are going to the activity coefficients. So activity coefficient means it's like we have some gases with ideal properties. So what we are doing was excess properties is nothing but G minus G ideal or M minus M ideal. You have seen this already at residual properties. If you remember the residual properties, if I say MR equal to M minus MID, so these values, if you see it before, which we will talk with the PVT cases, in the excess properties, we will do with the pure liquids and the activation coefficients. Activation coefficient is nothing but how much it is changed from its initial state to the final state. So these are the two differences between these two equations, the excess and residual properties. So now we will try to have that. Yeah, the following class we will try to do this one. The equation name is, one second, give me 1 minute. Redlich-Kister series. So we know Gi equals to, just let me from I will make it like this. From Lewis-Randall rule, we know that viscosity coefficient of any gases is equal to mole fraction of this one. So we know that, just let me know if you have any doubts in the equations, okay? Fine. So if I take ideal gas situation, it will be of so now G minus G ideal equal to RT ln of F1 cap minus So any doubts up to here? G ideal. Hello.
Yes.
Any doubts up to here? I think this is the one which is already discussed. So you already know that. So this equation also you already know. Ge by RT. If I differentiate Ge by RT, we got the final form. If you remember the last class, we got You remember this equation?
Yes, sir.
Okay, fine. So from this equation, if I take the closed system and if I take not only the two components, if I take, say, suppose multiple components, so then this equation will become this square dt plus sigma of t log dni by rt get cancelled. So now this equation will be like equals to d of g by rt at constant temperature comma x, then minus h by plus h by rt equals to minus t by d of g by rt p comma x. Now ln I equal to so you know these three equations, right? Any doubts in this three equation?
No, sir.
Okay, fine. So now what we'll do was in the next condition, so we know that delta G equal to G2 minus G1. If I take the molar frame, this will be the case, and you know that mu I is nothing but mu I star plus RT ln, where we are talking about the structures of ideal gas and the real mixture. So we all know that the whole total mole fraction equal to n equal to ni into xi. So if I do it, and you all know that G2 equal to sorry for the this one, yeah, G2 equal to G is nothing but as we already discussed that molar fraction of any partial molar property of any other extensive properties is nothing but the partial molar. Suppose if I talk about the enthalpy, partial molar property of enthalpy is written as Hi, but as we know that the chemical potential is nothing but the partial molar property of Gibbs energy. So from here I have taken G2 equal to sigma of Ni mu2 minus mu1. So you can think about what happened to the T and P. So we are discussing all these at the constant temperature and pressure. So what does it mean was, so I have taken one beaker where I kept the temperature and pressure as constant, and then we are mixing the things and we are keeping at the equilibrium and we are finding out what is happening. So we all know that for the combining with the ideal gas, we know that mu I is nothing but mu I star plus RT ln xi. Here ln x mu I star is nothing but the pure gas system. So if I take the both cases, the equation 1 and equation 2, you can get the delta G by n is nothing but RT ln sigma xi. From this you will get it from here and here. So once you have that, so when I am coming over the excess quantity, so what do you mean by excess quantity was, so when I have taken so you can see that formula of excess quantity is nothing but m equal to m minus m id, m ideal. So if you see, this is the same property as a residual property, where a residual property, if you see in the old classes we have discussed that mr equal to m minus m id. So here also it's same, but the things which we are discussed in the residual property, that came through the function of pressure and volume and temperature. But here what we are doing was, we have taken a bowl where we have the pure liquids, and then we have making it a mixture. So what we are going was, from here to here, say when it is in the pure, it is like take the consider as situation of ideal gas. So what we are going to at the end, whole topic was to discuss how does the variations occurs in the fluids when it is mixed from the irrespective of from the its pure liquids. So that's what, if you see, we have the equation of sigma ni xi. This is equation as we discussed for the Gibbs energy. We have made it as for the whole. They both are same. So once we have the same, here you can see from here this equation. So you got the sigma xi minus sigma xi ideal. For that, to make it the better clarity, I have written it here. So you have this equation sigma xi minus xi ideal. So what I added was, I added and subtracted the pure liquids to distinguish it from the ideal and the normal mixture. So So then I added and subtracted it, so we got it sigma of xi mu of mu I minus I. It is nothing but a mu I, which is in the mu mixture, minus mu I star. Once we are talking about the mu I star, because the partial molar property of the pure liquids, and minus mu ideal, and it is an ideal case, and this one. So this is the equation which we are focusing on. If you see here, this is the equation for the last 15 minutes I am talking about, which tells that okay, I have the solution in two frames. One, when you are talking about the ideal gases and the mixture, how does it vary? So that is called the excess property. So suppose let us consider we have taken the case where I have taken the case of two components, which is AL and AL, BL, and the gas and gas phase. So now before going into the talking about the what is the equation name? One second. Redlich-Kistler equation. Before talking about the Redlich-Kistler equation, I want to tell that suppose you have taken a liquid component, a component which is in the two phases. One is in the liquid phase, another one is the gas phase. What you will understand was what you will understand was when you are going from the liquid, if you see the potential energy, you know basically it is nothing but a kinetic energy plus potential energy. When you consider the gas molecule, so when you consider the gas, the molecules will be randomly distributed with maximum disorderness. So what happens was, so there won't be any internal interaction between the two molecules, and there won't be any much interaction of van der Waals and electrostatics. So that's why we consider the potential energy as 0. So here for the gases, it is mostly U equal to Ke. But when you come to the liquid, we have the molecule in the boxes. So here if you see, we have the molecules here where we got it, the molecules will be disordered, but it will be less disordered compared to the gas, and it will have the intermolar interaction between the A and B molecules, and there will be van der Waals forces between that two. And these properties we will talk about it. These properties, when you are talking about the van der Waals and all this, then the potential energy of the whole system will always be in the negative term. So the potential energy occurred through intermolecular interaction, the van der Waals forces, and the Coulombic interaction. This all the terms we will discuss much more in the statistical mechanics. As of now, just remember that potential energy will be less than 0. So if you consider it, then the UL is always less than 0. So how it is getting less than 0? So that's what I am explaining it here again. I think this idea is clear, where you have the potential energy equal to bonds, angles, and VW. And this, just for now, understand that internal energy of liquids will always be less than the gases. From this component, what we have done was, I made one formula. Mu of partial property at the pure liquid form is equal to the partial molar property at the gaseous state plus AA. So basically, if you see the books, the AA will be written as KAA. So for the better understanding of us, we can keep it as a intermolecular interaction. So as the intermolecular interaction will be in the negative energy, so it will give the mu naught equal to, so suppose if the value is 5, here the value will be minus 2, so we will get 3. So that's what it still follows the same case, mu L is less than the mu G. So here it is. So as we already discussed, here we have the two components A and B. So we have derived the two equations. Equation 1 for the partial molar properties of a pure liquid, and the same thing for the B is not UB, so it's not partial property, it's internal energy, partial molar internal energy of the B, and partial internal energy of A at pure liquid and pure liquid. So in the mixture, so suppose if I am talking about the mixture, what I have was, I have A and I have B. So now I am mixing it both. So when I am mixing it both, I have the A molecules and the molar fraction of A gas phase. So what we can do was, one second. Sorry. So what we will do was, what I am doing was in the mixture, when I am talking about the mixture, what does it says was, so I have taken the beaker, as we discussed previously, we have A in the liquid form, A in the liquid form, B also in the liquid form. Discuss that you know that we have the two mixtures, one is A and one is B, and A is in the A, B are in the where we have the two component phase, as we discussed. So as we discussed in the previous classes also, basically what we are doing in this class was, we are doing for the vapor liquid equilibrium. So that's why we are taking the two components which are in the vapor and liquid phase, and you can understand that there are two types of pure liquids. One is mu a star A and mu a star B, and then mu a star A and mu a naught gas and mu a naught B. As we discussed earlier, if we consider the mu, we know that, as we discussed recently, that mu L is always less than the mu naught because of the potential energy of the molecules. So once we got it, so we have the equation of mu a star equal to mu a naught plus AA. AA has been written as for the convenience of our understanding, so which can be written as intermolecular interaction, which is nothing but KAA. So we have that for the two liquids, for the two pure liquids, we have written the internal energy, the partial molar internal energy of the pure liquids as written in this form. And then we have the mixture. So what does the mixture was? We have two liquids, and then we mix the two liquids into single box where we have the A, B and AB. So now we consider in the A, B and also in the gas phase. So we already discussed that the gas phase, uh, the volume of the single particle will be very huge, such that there won't be any interaction between the particles of gas particles. So that's why we are not considering the interactions in the gas phase. So we are considering the only interactions in the liquid phase. That's why NaUA. So we are taking the NaUA plus NbUb plus NaXA KAA plus NbXb KBb plus NaXb plus NbXa KAB. So what does the equation says was? So we are considering the properties of NaUA, which is in the gas phase, number of particles of B in the gas phase, and then I have taken the A. What are the molecules which have the intermolecular interaction of A liquid with the A liquid itself? So it says how many neighbor atoms of A are there. So that we will focus on NaXA KAA. And the same thing for the BB also. So once you have when you are mixing at a constant temperature and pressure, there is a B and then there is a AB. What does the AB says was, okay, how many B particles are surrounded by A to have the interneighbor interaction, because we already considered the AA interactions through KAA. So now we are considering the KAB. So where we will focus on the how many moles of A has been closely related to the B, and then similarly in the vice versa of how many moles of B has in similarly interaction with A. So that's what you can see through the diagram also here, which we are showing. So AA, how many molecules of A is interacted with A, and how many B is interacted with B. So this equation, for our understanding, I have written it again nicely, where you can see NaU0 plus NaB0. So now for the further, okay, I have this equation where now I can make it as equation. So you can see the blue mark here, where we know that Na equal to where we know that XA equal to mole fraction of A equal to total number of moles divided by total number of molecules of A divided by total number of molecules. So before going to this, I want to make what is the change in the U mix. So what we are taking was, so initially the fluid is at the pure liquid. It means we have the pure. So okay, what I will do was, so now what we can discuss was, so we have the U mix. So I like the new color. So this was the notes which I made. So now what I want to talk was, so we are focusing on the delta U mix. So what do you mean by delta U mix? Because say suppose I have the system, initially I have the, so what I say, so initially we have the pure liquids. So after mixing of these pure liquids, what is happening was, we got the mixture, and we need to see the difference between this mixture and the pure liquid. So that's what we are going to figure out. So that's what we are going to write, the mu mix minus the pure. So that's what we are going to find. So previously we got this equation, and from the previous equation we understood that. So I will rewrite this equation, mu mix equal to, from this equation, if I keep together, if I keep this one as NaUA naught plus NbUb naught, this is, if you consider, this is for the gas phase, plus NaXaAA plus NbXbBb. This is regarding your molar interaction of AA and BB, and this term is for the molar interaction of AB. So once we have this equation, and we know that, okay, what we want to find out is the difference between the mixture and the pure liquid. So what I have done was, I have taken the initial equation, so this equation, which we consider as mu a naught, mu a star equal to mu a naught plus AA. As of now, just remember this equation, because we understood that mu L is less than mu A. So how it is less than, how it is not mu, internal energy, how it is getting less than mu, we will discuss it in the statistical thermodynamics. So what I did was, so we can write this equation as UA naught equal to UA star minus AA, right? I did the same thing here. So I have taken UA star equal to UN naught plus KAA. So which I added the number of moles of A on both the cases. So what I did was, so then this equation I can be written as NaUA naught equal to NaUA star minus NaKAA, and this equation can be written as so yeah, I have taken these two equations. So I have taken these two equations, number one, number two, and I uploaded in the space of here and here. So what I get was, so if I upload it here, so the whole equation is converted to this one, and the B equation is converted into this way, and the remaining AA interaction and the BB interaction and the A comma B, and this is the pure liquids, pure liquid of A, and there is a pure liquid B. So you can see that NaU star and Na star that get cancelled, and NB UB get cancelled. So then the remaining part we have written with the taking the common in terms of, now I written this is delta U. Sorry for the clarification. This is intermolecular interaction, and I want to keep this equation in terms of function of intermolecular interaction. That's why I taken the AA, BB, and AB. So you can see that, and we have the two different properties from the molar reaction. If you know, we know that XA plus XB equal to 1, which is XA equal to 1 minus XB, or we can write it as, in other words, we can write it as minus XA equal to XB minus 1 and minus XB equal to XA minus 1, because we have terms of XA minus 1. So what I have done was, I have rewritten the whole equation. First I have taken this equation like NaXB plus NBXA, and then I taken the KAB plus I just rewritten the equation. So now what I have done was, XB equal to, we know that NaXB is nothing but Na into NB1, so I have written this here. So this term will become as, and the XB, this will become as, and here also it will become as. So as I already said that we are writing the internal energy in the functions of the intermolecular interactions. So now when we got this equation, so you can see this one. So what I did was, to understand per mole, what I did was I differentiated, divided by n. So now we got 2 into Na by n. So if I take this as one term and this as another term, and here also this has one term and this has another term. So what I get was 2 into XA XB KAB minus XA XB KAA minus XA XB KBB. So what I do was, I take XA XB common. So now if I make the equation, so delta U mix by N equals to this one will come here. So that's what we have written it here. And then, so from the legendary transforms in the last class of, I think in the week 2, in the week 2 class, if you if you remember the week 2 class of legendary transforms, if you have any function f of a equal to ax plus by plus cz, then you can make new functions, f minus ax as new function, f minus by as new function, and then f minus cz as new function. In this way, we have taken this u equal to ts minus pv, and we made g as u minus tv plus pv, and we all know that at constant temperature and pressure, g equal to nothing but u. So that's what we will write as. So that's what we got it here, per mole. So once you know that, so here I will rewrite the equation. So we have g by rt equal to x1 x2 of 2 KAB minus KA minus KBBB. So this equation will give the Rutledge-Kister equation. So this and we know that in the second class we said about the power law in the last class, where we have x, y and multiplication of xy. If you remember this, we have 1, it will be 100, and if you have, so you reduce it to 48, it is increased to 2, so it is 96. So now you reduce it to 24, you increase it to I think 4, still the value is 96. You can see that even the higher decrease of x, the xy is not decreasing, but by the increment of y, the value of xy is still significant. So that's why we can say that x comma y, we can write it in the functions of y. So then xy equal to a plus by plus cy square. So this is how they will write. So that we written in the power form of g equal to xa xb, which is nothing but you can write also as x2 x2 into, as power form if you write a into, and we all know that from the power law these two are the independence of temperature and pressure. So that's why we write an final equation as equal to y, where y stands for a plus b of xa minus xb. You can consider that okay, there is a c term, the higher degree order also, but when when what we have done was, what we understood was, when in thermodynamics, when they correlate the formula with the experimental data, what they find out was even the 1 degree of 1 order is enough to match the correlation data. So that's why they got this equation. So once they got this equation, they have made it in the form of this, you can see, and now they made y as new name, a naught plus sigma of n equal to 1 to an zn. So if you just assume that n equal to 0, then y equal to a naught, which is nothing but y equal to a, and if n equal to 1, then it will be y equal to a naught plus a1 into z. Z is nothing but x1 minus x2. So I think this is clear from this side. So once you have these equations, and then from the partial molar property of the last week, we figured out that if you want to figure out the partial molar property of m1 bar, from the last class we derived this, and the same thing for 2 bar also, I think. So I use these two equations to represent the g of 1 excess Gibbs energy. It is equal to g of, so that's what we have done it here. And if you do it, and you know that, so I will do it here as there is no space. So d of g by rt is nothing but d of x1 x2 into y. So I will apply uv rule, which says that x1 x2 by dy by dA with respect to x1, right? We have done with x1, plus here y will be common, then again I will apply the dv rule, so which says x2 plus x1 into dx2 by dx1. So now this will come as 1 minus x1, so where you will get so that's what we have written here. And this one I can understand this equation from here. So once you have this, so I will explain it again. The fugacity value is nothing but gt equal to RT ln 1. This we got it from the Fugate equations and Lewis Randall rule, where we know that. Okay, so now what we will do was, we will write it as, so now we know already for this from molar equation. So now what I can write it was, sorry, so now this will become as, from this we will get it from here. So this is nothing but x1 x2 y plus x2 into x1 x2 y so this is the equation which we are talking it here. So further, if you do it for the ln of y2 also, you will get, so we know that from the partial properties we have carried out that m2 bar equal to m bar minus x1 dm bar by dx2. If we apply, we will get this equation, and we are so okay, I will explain it again. So we know that, so in the in the last class you have seen this equation, right? G of E equal to RT A21 x1, okay, A21 x1 plus A12 x2 of x1 x2. So what I will do was, so for this, to understand this equation, I am making two assumptions. So now I apply the two assumptions in the equation. So now what we will get was a0 plus a1 into x1 plus a0 minus a1 into x2 of x1 x2. So now what I will do was, I will keep it like this. So now I will explain, sorry, now I will explain only this, sorry, now I will explain only this one as 1 minus x2 plus a1 of 1 minus x1. So now what we will do was, sorry for the disturbance, so what we will do was a into a0 minus a1 plus ax1. So if you see, this get cancelled with this and this, so we got a0 minus a1 of x1 x2. So this is nothing but, you can see it from this one. So what we will do was, so we are writing it as, yes, a0 minus a1 of x1 x2. So it is nothing but g by rt equal to x1 x2 into y. I think this is the equation, if I am not wrong. Give me time, 1 minute, I will recheck it. So from here what we got was a0 x1 plus a0 x1 minus a0 x1. So a0, yeah, we got a0, yeah, I think here, from here what we do was a0 x1 plus a1 x1 plus a0 x2 minus a1 x2. So this will be as a0 x1 plus a1 x1 plus a0 minus a0 x1 minus a1 plus a1 x1. Sorry, this is the one can get cancelled. Then this is, so then we have the equation of 2x1 minus 1. So this will be in the form of x1 minus of plus minus 1 is equal to this is nothing but y. So now Ge by RT equal to x1 x2 into y. So this is the equation, so which we saw it in the class of the sort discussed. So once we have this equation, so then we know what to do. So then ln 1 equals to, so now if you want, I'll so what is the ln 1 equation which we have? Ln 1 equation which we have was x1 x2 of y plus x2 of x1 x2 of dy by dx1 plus y of, I think, x1 minus x2 minus x1. I think this is the equation which you have. Yes. So from this equation we can derive it, x1 x2 y plus x1 x2 square by dy by dx1 plus x2 square by y minus x1 x2 y. So this will get cancelled, equal to, if I take x2 square common, 1 by x plus y. I think this is the equation which you will see it in the class. In the same way, if I do it for the ln y2, you will get the equation of x1 square of y minus x2 divided by dx2. This is nothing but Margulis method. So once if I go, say suppose if I am going through the ln of y to infinity, it means v1 to infinity means it will be x1 to 0. So if I go x1 to 0, then we have ln of. So we'll try to expand this equation first. So before writing this equation, what we can do was just try to expand this equation in terms of a naught and this. So now this will be as ln of y1 equals to x2 square of a12 plus 2 into a21 minus a12 into x1, and ln of y1 equals to x1 square minus a21 plus 2 into a12 minus a21 into x2. This is also this Langmuir model. So then when v1 tends to infinity, which means ln of v1 tends to infinity equal to a12 as x1 tends to 0, x2 tends to 1, and v2 tends to 0, ln of v2 infinity equal to a21, as x2 tends to 0 and x1 tends to 1. So these all are the Margulis method. So once the Van Laer equation, to discuss more on the Van Laer equation, there is nothing but what the Van Laer equation was done was, so if you see the Redlich case run, so now the Van Laer equation was carried out like this. Van Laer equation was carried out like by GE by RT equal to a dash by d dash by y. So y is nothing but x1 minus x2. So then you can understand the whole formula. Then from the Van Laer equation, we will get ln of y1 equal to 1 plus a dash x1 divided by a dash 2 minus 2, because we are doing the reciprocation of the what we have done for the Margulis model. So this is equal to a dash 21 of 1 plus a dash 21 to x2 by a12 into x2 into minus 1. So we can do for the Wilson equation also. So the Wilson equation also has the two components, which is a12 minus x2 ln of x2 plus x1 ln of a21. As this n tends to infinity, this equation will go as ln of plus 1 minus a1, and this infinity goes to minus ln of a21 plus 1 minus a12. I think these equations are clear, and if you have any doubts, we can discuss in the next class. Thank you for attending the class. And in this today's class, what we have discussed was phase equilibria, vapor liquid equilibrium, Raoult's law, and expression using Raoult's law and Dalton's law,